So today we will discuss some problem which we can solve by Lagrange equation, and then we will solve the same problem by using Hamilton's equation. We will see, we will get the we will get the same equation of motion, uh, whether we use Lagrange equation of motion or Hamilton equation of motion. So these two methods are actually equivalent, we can show there. So it is your convenience which method you like to choose for a given problem. At the end we will get the same equation of motion. So let us consider first problem. So first problem is here is a mass spring system where we have a mass m is tied with a spring on a horizontal surface, and when you pull from its equilibrium position, this is equilibrium position, right? Then when you pull suppose along this direction from its equilibrium position and release it, then it will oscillate horizontally, right, along this direction. So we know its kinetic energy is half this x dot square, half mv square, and v is nothing but x dot square. This x dot means the first derivative of time. So this is kinetic energy, and this potential energy will be half kx square. So this is the by Hooke's law we can determine the potential energy, right? We already know Hooke's law is minus kx, where k is spring constants, right? When you pull x length, so it will, right, from its equilibrium position it will oscillates about its mean position. So this is the potential energy we can use by using the time derivative of this potential, right? For a conservative system, this force is equivalent to the gradient of some potential. So here this is v. So our Lagrangian will be t minus v. So you can just put these values of t and v here and get this Lagrangian. So when you calculate this del L by del x, you can get x here, right? Here our x is the generalized coordinate and x dot is the generalized velocity. So when you take the derivative of L with respect to generalized velocity x dot, you will get mx dot, right? And when you take exact time derivative of this derivative, partial derivative, we will get mx double dot. So our Lagrange equation, you can write our Lagrange equation like this for a conservative system. So you just put these two values here and these values here, you get ultimately the equation of motion, right? And we can define another parameter, right, omega square, which is angular frequency here, whose values will be root over k by m. And this is the equation of the simple harmonic motion, and when we integrate twice, you will get the solution of this equation, right? So this is x is equal to x naught cos omega t plus phi, where x naught and phi are the integration constant, are the initial conditions of this problem, right? So so this is the cos function. So it is the oscillatory, right? And we know when we solve simple harmonic motion, we generally get cos function or sine function, right? Sinusoidal function. So are the combination of both this sine and cosine function. I just considered it this cos function. You can take any one of these solution, right? So let us consider next problem, which is simple harmonic motion, right? So simple harmonic motion. So here we have a bar pendulum, or sorry, here we have a bob which is hang about a point, and when you disturb from its equilibrium position, right, so it will oscillate, right? So again we can write its Lagrangian by calculating its kinetic energy and potential energy. So let us consider so in Lagrange method, when you calculate potential energy, right, you define, you choose a origin of your convenience in the problem. Here I have considered this point as our origin. You can take this also. So at the end you will get the same equation of motion, right? So but for this problem I have considered this is the equilibrium position, right? So so at this point, so this is general xy point here, this is our xy point when we disturb from its equilibrium position, right? And so this is the at any time t, the position of the bob will be at here, right? So let us assume its velocity at this point is v. So so we can write this velocity in terms of its component along x direction and y direction. So vx and vy are the components of v along x and y direction, right? And let us consider L is the length of the string, right? And this string is inextensible, right? So the position of this bob will be xy. So this is our x and this is our y. So you have to find this distance, right? Either this one or this one, both are the same. So we can consider this angle is theta, right? So this is again the length L, and when you take, right, component of this along vertical direction, you will get this L cos theta, right? And perpendicular component will be, this is L sin theta. So L sin theta. So this x component will be x L sin theta, and y component will be this, which I have considered here, h. So h will be this total length minus this length, right? This is our horizontal component which we have taken. So this will be L minus cos theta. This is our h, right? This is our h. Here I have written here, this is our h. So you can consider the x component of the velocity vx is equal to derivative of x dot, which is equal to, right? So which is equal to this L derivative of this function. So this is L cos theta theta dot. And similarly, when we take the function of when we take the derivative of this h with respect to t, we will get L sin theta d theta dot. So the velocity, so the resultant velocity will be root over vx square plus vy square, and when we put these two values, you will get this L theta dot, right? Because sin square theta plus cos square theta will be 1, right? So this is our velocity. So we can write its kinetic energy will be half mv square. So v is we have calculated already. So this is equal to half and L square theta dot square, and potential energy will be mgh. So h is here. So mg h L minus L cos theta, and when you take this L common in the above expression, you will get 1 minus cos theta, right? So here I have used other way to calculate the kinetic energy, but right, because there are two ways to calculate it, but I will not discuss this way of calculating the kinetic energy. We will discuss later in some other videos, right? So the Lagrangian will be t minus v. So this is our t and this is our v, right? So you can now identify this generalized coordinate and generalized velocity. So theta is here our generalized coordinate, and theta dot will be the generalized velocity. Other things are constant, right, in this Lagrangian. So right, so when we take this partial derivative of L with respect to theta, you get this. mgl, and when you take this derivative, this will be sin theta, right? And when we take the partial derivative of this L with respect to theta dot, you get ml square theta dot. Now our Lagrange equation of motion for the conservative system will be d by dt of del L by del theta dot minus del L by del theta dot is equal to 0. Now put these values of derivative, both the derivatives, in this Lagrange equation, right? So this becomes ml square theta dot, and this will becomes mgl sin theta. This m and this L right will be cancelled out, and we are left with the single L theta double dot and g sin theta is equal to 0. So this is the general solution of the simple pendulum, right? But for a small angle, we can write sin theta is equal to almost theta. So the above equation becomes this, and when you take this L in the denominator, this becomes this, and we can define a new function or new variable omega which is equal to the under root of L by g, and this omega is the angular frequency. So this is related to the time period, which is equal to 2 pi upon t, right? So the time period of the simple pendulum will be t is equal to 2 pi root over L by g, and you can again now identify this is the equation of the motion of the simple harmonic motion, and its general solution will be again a sine function or cos function or the linear combination of both. So I have written here this theta is equal to a sin omega t plus phi. Again this a and phi are the initial conditions, are the integration constant, because this is the second order differential equation. So when you integrate this equation twice, you will get two integration constants. So a and phi are the two initial constant, and they have the meaning of this amplitude, and this phi has the meaning of the initial phase, and this is the maximum amplitude of the, right? No, so this is the amplitude at time t equal to 0, right? Right. Now our third problem is Atwood machine. So here we have a pulley which we have considered it is a massless, and it is also a frictionless pulley, and we actually hanging two masses of values m1 and m2 on opposite side, right? And we also consider the length of this rope is L, and this length of the rope is L, which is inextensible, right? And for this problem I have chosen again this horizontal line as the our reference potential, which we have taken 0, right? And when we move downwards along this direction, I considered it is a positive direction. So for convenience I have chosen this is our positive x direction. So this is the our reference potential, and when you go down, the potential energy will decrease, right? Because this x is positive, so the potential energy will decrease with downward, in the downward direction. So the potential energy will be V equal to minus m1 gx. Here I have considered the length of the rope in this side is equal to x, and for this right hand side it is L minus x, in such a way that when you add these two lengths, you will get L, total length of the string, right? So if this is x, this will be L minus x. So the second term will be minus m2 g, and this is L minus x, and the kinetic energy is T is equal to half m1 plus m2 x dot square, right? So kinetic energy will be you can calculate, right? So kinetic energy will be like half m derivative of this x dot square, and for this when half m2, and when you take this derivative of this term with respect to time, you get minus x dot, and when you square it, you get x dot square, right. So I have done in shorthand manner, but you can calculate it very easily. And now we can write our Lagrangian, which is nothing but equal to t minus v. So t is here already calculated and v is here. So now you can identify again here x is the our generalized quadrant and x dot is the our generalized velocity. So when we take this partial derivative of L with respect to x, we will get m1 minus m2 into g, and when we take this del L by del x dot, right, only this term contribute, and this will get m1 plus m2 x dot. Now our Lagrange equation of motion for conservative system will be this, and now substitute these two values, right, here and here, right. So you will get m1 plus m2 x double dot minus m1 minus m2 into g, and when you write this x double dot, it will be m1 minus m2 upon g upon m1 plus m2. Now you can consider here two cases. If m1 is greater than m2, so this is the acceleration, this is double time derivative of the position, right. So this, if m1 is greater than m2, this acceleration comes out to be positive, right. This is our positive direction, and right, this is our positive, because we are assuming when we go downwards x takes positive values, right. So acceleration will be positive, and it is very intuitive, right, because if this mass will be larger than this mass, this will go down, right. So this is the direction of the acceleration. And when you take the other condition, when m1 is less than m2, this acceleration will be negative, and it is, yeah, we can easily say, because if this is smaller than this one, so it will go downward opposite to the direction of positive x, right. So therefore the acceleration will be negative, right. So in the next video we will see these three problem by using the Hamilton's equation of motion, and at the end we will get the same equation of motion, right. Thank you.